Hello everyone, my name is Miodrag and I will present the paper Comparative Analysis of Techniques for Testing Object-Oriented Programs, which was written by Tamara and myself. So what is at the beginning software testing? So it is a set of activities which we usually perform in order to either find the bugs in a program or to assure that the software actually behaves as it was specified. It is generally a part of a broader discipline which is called the quality assurance, which is wider, of course, than the software testing, and it has the main goal to assure that the software which we are developing will be adequate in terms of quality for the customers, and also that it will be delivered within a reasonable and defined deadline. So it's not acceptable that we are building the software which cannot be delivered within some normal time range, because if we are late 1 year with our software, it's not good for the customers. So it must be able to be delivered within a reasonable time frame. And therefore, it is directly connected to the customer satisfaction. Actually, our software will not be accepted by the end users if the application is not doing what it's supposed to do, or it has a lot of bugs, or it's not pretty enough, so no one wants to use the ugly application, or it has a poor performances. White box techniques are one of the major group of techniques which we are using often to test our software together with the black box testing. And the white box is mostly used to, number one, verify that the code is working properly, and number two, to measure the test coverage. So to measure how well we covered our code with our tests. The white box, by definition, assumes the access to the source code. So we are able to see the source code and to see the internal mechanisms and structures which are used in the components which are currently under testing. And we use a different code metrics and measurements to describe the degree of our testing. So the level, how good we have tested our program. And the most frequently used techniques and measurements are the statement coverage, decision coverage, and the path coverage. And when we are talking about the white box testing, so the program is usually represented in the form of CFG, or the control flow graph, which is used to describe the logical structure of the code. Usually we create a vertex for every instruction in our code, and we can see easily the branching in our code, because if we have, for example, the if condition, we will have branching, so two edges will leave that node with the if statement. And we use this graph when we draw it to select the tests. When we talk about the object-oriented programs, so it is still that the most of the techniques which are used for the traditional structural programs are still in use for the object-oriented programs, and that's perfectly fine, because those techniques are already around for some quite time, and they are considered to be de facto standard. However, due to the nature of the object-oriented programs, they are much complex than the procedural programs, in terms that we have some additional concepts such as classes or inheritance, encapsulation, polymorphism, and of course dynamic binding, which is the biggest problem, and the term of the abstraction. So the main idea is that we can apply the traditional procedural techniques, but we must also take into the consideration the abstraction. So all of these terms which are brought by the object-oriented program's nature. And there are several approaches which can be used for testing object-oriented program, we have selected and compared two very common approaches. So we selected the approaches which are most in use in the practice, and we tried to apply them to the same example. So we have implemented the object-oriented program sample and tested both selected approaches against this program. We have chosen the McCabe technique for object-oriented programs, which is the traditional structural approach with the aspect for the object-oriented programs. So with the addition of properly testing the abstraction, and we also selected the extended control flow graph, or ECFG. We selected them because of their, of course, importance and practical applications in real-life projects. So we have started with the McCabe's traditional approach. So this is de facto standard, and the measurement or the symptomatic complexity which McCabe introduced has been de facto standard in a large number of software development companies, and it is used to measure the complexity of the code. For example, some big companies don't allow that their methods in their programs have complexity more than 10. So complexity more than 10 means there is more than 10 paths through that method. So usually the complexity of each method should be below 10. And in the same document or the paper McCabe published, there is also the description how to test the object-oriented programs. So they are defined together, and they are widely used on all types of software, of course, including object-oriented software. And the ECFG is the novel approach, which was based on the McCabe's traditional approach, so the structural approach, and it's combined with the object-oriented nature of the software. So it's a bit more novel, and we tried to compare those two techniques because also they are most commonly used in the practice on the real-life projects. We have created a simple program which implements both inheritance and abstractions and try to see how well both techniques behave in case that we have the abstraction in our program. And we have generated the test set according to the rules of each approach. So we have strictly followed the rules defined by the McCabe's technique and by the ECFG technique. And we compared the test set which we got. We compared their quality and efficacy in terms of the required number of test cases for covering all the items required by the technique, and also the test coverage. And we used the mutation testing tool, PIT tool, for code coverage analysis. So I will now just briefly introduce the object-oriented approach for both techniques. So McCabe's approach actually is considering the implicit control flow on method calls. So first of all, methods in object-oriented programs, because I have already said it, usually tend to be really simpler than the traditional functions in the traditional procedural programs. Therefore, the unit testing is usually relatively easy, and you can apply directly all the traditional techniques used for the structural programs, also for the unit testing of object-oriented programs. So far so good. However, when we come to the polymorphism and inheritance together with the dynamic binding, it will complicate unit testing exactly due to the implicit control flow. So what is the implicit control flow? So it is the case, the special case where we have in object-oriented programs that the object variable can hold the object belonging to the given class or any of the extended classes. So this is the situation that we can have, that inside one variable we can actually have objects belonging to different classes. So the problem is, if we call a method which is overridden, so with which actual version of this method will be called is not known during the compile time. So it's not the static binding. So that's why we call it dynamic binding, because it will be determined dynamically during the runtime based on the actual type of the object which is placed in this reference. And we don't consider this implicit control flow on the unit level, because there is no much sense to do it. You need to have the complete hierarchy of classes for testing the implicit control flow. So we apply it in the integration testing. So when we talk about the integration testing, in the simplest form, it is just the application of the traditional testing used for the procedural programs. However, we must also consider the implicit method calls. So this is the situation where we call the overridden method, and we must see which actual object is placed in this variable, so that we know by dynamic binding which version of the method will be actually called. So when we talk about the McCabe's approach, there is three possible sub-approaches: optimistic, pessimistic, and balanced. So optimistic approach will check at least one resolution, method resolution, on every method call location, and it also requires that every method resolution should be verified by at least one call. It's optimistic in terms that if we don't find any errors, we assume that all other combinations are valid as well. The pessimistic approach will assume that we have the negative impact on the code, so it will require that we check every possible method resolution on every method call location. The problem, it can lead to high testing complexity and large number of tests. And the balanced approach is the compromise, of course, where we actually check all possible resolutions on one method call location to gain confidence in abstraction, and we expect that all other resolutions will be valid as well. So on the other method call location, we check just one resolution. With the ECFG, on the other hand, we tried to represent our program with the multi-layered graphical model, and this model actually has the collection of the CFG, so the control flow graphs for each individual method of the program. So each method is tested as the procedural program with its CFG, and we actually have two layers. So on the top layer, we have the methods of the individual classes, and the second layer actually represents the individual CFGs of these methods. So it is similar to the basic CFG in terms of vertices and edges, except for the top layer, where some of the vertices doesn't need to be connected. So the vertices on the top layer will be connected if there is a method call between two methods. So if method one calls method two, we will have edge between those two methods. So nodes actually represent methods. Each method, of course, has its own CFG, and it can be calculated for the cyclomatic complexity. So we have edges between the vertices if we have the method calls between two methods. And the overall complexity of the program, which is in this term referred to as extended cyclomatic complexity, has different values based on some 6 different cases which this approach considers, and which are mentioned in the paper itself. So let's see what code we have selected to use. So we use the simple program which was created for the purpose of the abstraction. So to test the abstraction. So we have selected the geometric shapes classes, system of the classes. So with the geometric shape abstract class at the top of the hierarchy, and two extended classes, sphere and cube. And we have selected it to be illustrative. Of course, it can be applied, so the logic can be applied on numerous real-life examples. So the structure with several classes with the same base class, which needs to contain common properties, which can be, for example, different classes of the users of the system. For example, for the student managing system, different types of students. So students of the master studies, of the doctoral studies, regular students, etc. I mean, the student abstract class at the top, which contains all the common properties for each students, or again, the hierarchy of the classes which represent vehicles or similar. So this is the actual UML graph of the observed classes. So we have the geometrical shape class at the top of the hierarchy. It is the abstract class, and we have two extended classes, cube and sphere. So the structure of the class geometrical shape is actually that it has some properties. It has some abstract methods which are actually required to be redefined in the extended classes, and we have one method which is inherited in the classes, extended classes, and used without any modification. So this is the method which calculates the density class for this concrete object. And we have the two classes, so the extended classes, sphere and cube, which of course give the implementation of the abstract methods which are defined in the abstract class, and also they are using this method which calculates the density class without any modification. So they give the implementation of free methods which are abstract in the geometrical shape class, because of course every geometrical shape has its own way how to calculate the area or the volume or the mass of the actual shape. And the main class actually just takes the two shapes from the user, and it calls the method which compares those two objects by their masses. So the method which compares the objects is this method. So it takes two geometrical bodies as the input, and it calls calculate mass on both of those bodies. And in case of course which mass is bigger, it will return the bigger object. So on the unit level, so both the classes sphere and cube actually require 10 tests to cover all the basic paths through all the individual methods. So actually it is just the application of the traditional path coverage McCabe's technique. So when we observe the main class and the method which compares two objects, we actually need two tests. So in order to cover all the paths. So first test, which will take that the first shape is heavier, and the second test, which will take the second object as the heavier, so that we can cover both branches of the if statement. And these are example tests, two JUnit tests for covering this method, which takes two cubes. In first case, of course, first cube is bigger and heavier, and second case, the second cube is bigger or heavier. And now we have finished with the traditional techniques. So now our code is 100% path covered. However, we need to also consider the abstraction. So we have selected to demonstrate the optimistic and pessimistic approach, more precisely in the case, because in this case a balanced approach is actually the same as the optimistic approach, which will not be the same if we have more than two classes extended from the geometrical shape class. So when we take a look at the tests which we have generated up to now, we see that we don't cover all the requirements for the optimistic approach. So optimistic approach will require that we, on every place of the method call, which is actually the calculate mass method, we verify at least one resolution. This one is fulfilled because we have called the calculate mass from the cube. However, it is also required that we verify every possible resolution with at least one method call, which is not fulfilled because we didn't, in the tests which are perfectly fine from the path coverage position, we didn't cover the resolution from the sphere. So actually, we would need to add one more test, which could actually be replaced with one of the already two written tests, where we could just require that one object which is passed to this method is the sphere. Of course, if the abstraction was defined in a different way, that we had more than two classes extended from the geometrical shape, it will actually require additional tests. But in this case, we just need to modify one test. And in this case, we have the optimistic approach fulfilled. However, we still didn't fulfill the pessimistic approach. This approach actually requires that at every method call position, we test every possible solution. So it will actually be required that we add one test where lambda will also be the same, the first parameter as well. So we can achieve this by just changing the test from the previous slide where we generated the test for the optimistic approach, and we would require that it takes two sphere parameters. In this case, it will also cover the pessimistic approach. So, of course, again, it is not required to add more tests to achieve the pessimistic approach. It is just enough to modify the one which we added for the optimistic approach. If there were more classes, of course, it will be required to add more tests to test every possible resolution on every place of resolution. When we consider the ECFG approach, we need again to unit test the sphere and ball, sphere and cube classes, and the tests are actually exactly the same. So chromatic complexity remains the same. So this part is perfectly fine. However, when we considered the method which compares two objects from the main class, it will actually be required to draw the ECFG of that method. So when we draw it, we see that the method which calculates mass actually uses two methods, calculate volume and the method which actually gets the density of the object. And according to the rules of the ECFG, total value of this method is 0. It means that we don't need to add more tests to the regular CFG tests, which we created by just plain covering the basic McCabe's paths. So the exact calculation is, of course, available in the paper. I will not go into details during this presentation. So the point is, for the ECFG approach, it is not required in this particular case to add additional tests. And actually, the tests for the ECFG approach are exactly the same as the structural tests which we mentioned before. So they don't mention abstraction. So the actual ECFG approach, by the definition in its original form, does not mention abstraction anywhere. So it is already a hint that this could lead to some problems with the abstraction. So basically, it does not require generating the new test cases in case of the overridden methods. And it is possible to be seen from the results. So if we see with the mutations of the code with the PIT tool. So if we test with the included all test classes, we see that the mutation result is the same. So there is no difference between those techniques when we include all classes in testing, because if you, of course, include the unit test as well, if there is some error in the extended classes, the unit test will see it. However, if we just observe the integration context, so this will mostly require just to run the tests from the main test class. So in this term, it will be the test which is testing the main and calculate, compare two objects method. We see there that there are some differences. So we see that the optimistic and pessimistic approach from the integration context achieve better results than the ECFG, which is actually expected because the ECFG does not require the abstraction to be tested in its original form. So it means that if we just test the method compare two objects with two, for example, cubes, it will be completely fine from the perspective of the ECFG. So if the error actually is in the sphere class, it will not be detected. So we can see that ECFG is achieving even worse results than even the optimistic McCabe's approach. So what we can conclude? We can conclude that the ECFG, which is not requiring the verification of the dynamic binding in the original form, will underachieve compared to both McCabe's approaches if the program actually contains abstraction. In this case, of course, we had one abstract class and two extended classes, and if the complex, if the actual inheritance structure was even more complex, the results will be even more drastic, of course. We must also note that in case of the program which doesn't include abstraction, ECFG can achieve better results. So this is another example where, for example, if we just use the traditional McCabe's approach, it is required only to cover basic paths. So as ECFG will actually require additional tests if, for example, on some paths we have a method call which has the cyclomatic complexity more than one. Sorry. So in this case, of course, ECFG could show better results. So because it will require additional tests and it would expose some hidden errors. But in case of the abstraction, which we consider in this paper, we saw that the McCabe's both approaches show better results than the ECFG. So for the questions which were asked, so first was to discuss the utilization of the continuous integrations in terms of facility testing and verification of the principles in object-oriented programs. So first of all, what is continuous integration? So it is a practice where we require that all the team members integrate work frequently. So usually at least daily updates and daily commits of their code, which will lead to multiple integrations per day. And each integration will actually be verified by some automated build tool. So a lot of actual frameworks and integrated development environments have the possibility to do the automation build. And of course, it is usually also required to run all of the available tests. So after every commit, when the automated build is actually made, the complete test base will be run to detect integration errors as quickly as possible. So of course, this approach with the frequent integration and the test run is, of course, better because we can detect defects basically at the moment when they are introduced. So at the moment of actual integration and commit by the developer. Of course, it can be only done if the tests are automated. So because we will run, for example, JUnit tests, the set of JUnit tests after every integration of every commit from some developer. However, because it is depending on the quality of the tests, if we actually want to test properly the abstraction, it means that our tests, which will be automated and which will be run in every integration round, must be properly written in terms of abstraction, because if the tests themselves are actually not covering abstraction, the continuous integration is useless. It will not detect errors, and we are in the problem. The second question was that we reflect on the importance of the coverage in the object-oriented testing. So how do we assess the adequate coverage? So coverage is in general, of course, extremely important. So it is how well we have tested our program, how thoroughly we have tested our program. So it will tell us when did we test enough. So we usually cover some items in our code with the tests. So item can be anything, so either statement or paths to the code or some methods. And we tell that the item is exercised if at least one test has covered it. So at the end, if we don't have the 100% coverage, it means that we have not tested all items in our code. And if we didn't test some piece of code, we don't know if there is an error in it or not. So we must execute it in order to see if it's worked properly. So if the coverage is not 100%, it usually means that we must add additional tests to cover those specific items which were not covered before. So in the object-oriented programming, we still use a lot of traditional techniques. So the statement coverage and path coverage are mostly used, and most of the integrated development environments have the option integrated to see in real life the statement coverage. And also there are numerous tools which you can use for calculating the path coverage. And also another approach which is also used commonly in the metrics for the object-oriented programs is in case that the program can be modeled as the finite state machine, which we can basically cover with the tests the states and the transitions between the states. So for example, it can be used zero switch cover, which requires that every state in our program is visited at least once, or one switch cover, which actually requires that every transition also must be covered, etc. Thank you a lot. This was the presentation, and goodbye.